All right, in this video, we're going to look at infinite limits. First thing we need to note is that limit answers are sometimes a little weird. And here's an example of what I mean by that. Let's say that we have the limit as x goes to 0 of 1 over x squared. So we know that we want to try direct substitution for this, and we would type in, plug in the 0 for the x, and we'd have 1 over 0 squared, or 1 over 0. So in the past, you've been told that if you divide by 0, that this does not exist. However, that's not really what's going on with this problem. We plugged in 0 just to use the direct substitution method to try to evaluate it. But really what we're looking for is we're looking for a limit. So we don't want to evaluate this at exactly 0. We just want to know what's going on as it gets close to 0. So let's go over to Desmos and see what's going on. So I've got 1 divided by a small number. So 1 divided by 0.01, that's pretty close to 0, right? So notice that's 100. So I actually get a number out of this, and it's kind of a big number. If I start adding more zeros, if I add another 0 in the denominator, notice the answer went from 100 to 1,000. So if I add another 0, it's getting closer to 0, right? The denominator is getting closer to 0 if I keep on adding zeros after the decimal place. It went from 1,000 to 10,000. Add another 0, we're at 100,000. Add another one, that's 1,000,000. So the more zeros I add in the denominator, the closer that denominator gets to 0, the whole value of that fraction blows up to infinity. So we would say that this limit is equal to infinity. And actually, I just misspoke. So there's a technicality on the AP exam that if you say that something is equal to 0, that you might lose a point because of that. So the way I've been taught to do this is anytime you're going to evaluate something in infinity, use just an arrow to say that it's evaluating towards that, but it's not equal to that. The technicality is that you can never actually equal infinity. That might also be true if you are trying to plug in infinity somewhere in your problem. And here's an example of that. Let's say we have the limit as x goes to infinity of 1 over x. So my direct substitution, I would plug in infinity into this. And you're not really supposed to plug in infinity for x's and try to say that it's equal. But you could just throw an arrow in there and say, well, this is what follows from that. And if you do 1 divided by infinity, think about it. You've got 1 being divided by many pieces. Well, that fraction is going to tend towards 0. So that's equal to 0. So the different forms that that these limits can take that seem a little weird are these. And these I would say just to memorize. So if you have a fixed number that you're dividing by 0 as a limit, this is equal to infinity. And if you have 0 divided by a fixed number, well, that's just equal to 0. And then on the other hand, if you're using infinities, if you have a fixed number divided by infinity, that's equal to 0. And then if you have infinity on top, and that's divided by a fixed number, like a constant, then that's just equal to infinity. And of course, we know that if you have 0 over 0 or infinity over infinity, that those are the indeterminate forms. So you've looked at horizontal asymptotes in the past, but we're going to talk about trying to find a horizontal asymptote through limits. So the definition of a horizontal asymptote using limit is it's the limit as x goes to either positive or negative infinity of your function. So to find horizontal asymptotes using limits, here's what you want to do. You want to convert each term to 1 over x, or at least some variation of 1 over x, by dividing each term in your rational function by x raised to whatever the highest exponent is inside that function. The reason why we're doing this is because we can evaluate each of those limits separately. Remember, the limit as x goes to infinity of 1 over x, that's equal to 0. So you can evaluate all those guys separately and then that'll help you find the answer. So here's an example of that. Let's say we have the limit as x goes to infinity of all this stuff. So if I were to just try to plug in my infinity here, I would have a bunch of infinities divided by a bunch of other infinities. So I would basically kind of get like infinity over infinity. That would be indeterminate form. So what I'm going to do is I'm going to do what the note said, and I'm going to go through and I'm going to divide every single term by x raised to that highest exponent. And if we look through the problem, the highest exponent on any of the terms is cubed. So I'm going to go through and I'm going to do 7x cubed divided by x cubed. And then the next term is 5x squared. Divide that by x cubed. And then the 3. So there's our numerator. And then I'll go through and do the same thing for the denominator. 2x cubed over x cubed. 8x over x cubed. And 1 over x cubed. So I just went through and divided absolutely everything on the top and the bottom by whatever the highest exponent was. And now let's see what happens. So stuff is going to cancel out for us. So if I look at the first fraction, top left, I have an x cubed on top and bottom. So those are going to cancel out completely. The next fraction, I have x squared on top. Well, I've got x cubed on the bottom. So two of those are going to go away from the denominator. That third fraction on the top doesn't simplify. If I look at the bottom, x cubed would cancel on top and bottom, and then x on top would cancel with one of the x's on the bottom, so I'm left with x squared there. So if I rewrite this, I would have the limit as x goes to infinity of, so I just have a 7 there. There is no variable left. And I've got negative 5 over x plus 3 over x cubed divided by just the 2 plus 8 over x squared minus 1 over x cubed. Now, if you wanted to, you could use the quotient property from the limit properties, and you could also use the sum and difference property to cut this up into 6 different limits. You'd have 3 limits on the top, 3 limits on the bottom. But that's a lot of writing. All I'm going to do is I'm just going to go through and I'm just going to evaluate each of these limits separately as I plug in infinity. So I'm really just going to do direct substitution. So what I would get here, I'm being careful to use an arrow because I'm plugging in infinities, which I'm not allowed to do if I'm going to say that this is equal. So if I plug in infinities, I'll get 5 over infinity plus 3 over infinity for those. And then on the bottom, I just get a 2. And then I get 8 over infinity, and then minus 1 over infinity. Notice that, if it's 1 over x, that's equal to infinity. 1 over x cubed, that's equal to infinity. Infinity raised to any exponent is still going to be infinity. Well, any of these numbers that are being divided by infinity, those all go to 0. So in the numerator of my problem, I just have 7. And then on the bottom, I have a 2. So this ends up being 7 over 2. And that's the final answer. All right, so try this one on your own. Try to figure out the limit as x goes to negative infinity of this rational function. And then go ahead and pause the video and give it a shot. All right, so I'm going to do the same thing I did in the last problem. I'm going to look for the highest exponent, and then I'm going to divide every single term by x raised to the highest exponent. So the highest exponent I see is a squared, the negative 6x squared. So I'm going to go through and divide everything by x squared. Now that I've done that, I can go through and simplify some things. The top left fraction, I've got x squared on top and the bottom, so those are going to cancel out. And then the next one is, let's see. So then the next one is 7x over x squared. So that x on top would cancel with the 2 in the bottom there. And then the third fraction on the top doesn't simplify. On the bottom, I'd have x on top cancels with one of the x's in the bottom. And then the bottom right fraction does not simplify. All right, so let's clean this up. So the top left fraction simplifies to a 6, and then I have plus 7 over x plus 3 over x squared divided by 2 over x plus 5 over x squared. All right, so now let's try the direct substitution. So I'm plugging in an infinity, so I'm going to use an arrow here, being careful not to say that these are equal. And then I'm going to have 6 plus 7 over, this is a negative infinity, plus 3 over, well, this is going to be a negative infinity, and I'm squaring it. So if I square a negative infinity, that does actually make it positive. So it'd be a positive infinity for that denominator. And then in the bottom here, I've got 2 over negative infinity plus 5 over negative infinity squared. All right, so let's think about what all this stuff means. Well, if I have 7 over infinity, I know that that's going to be 0. And I know this is going to be 0. And I know this is going to be 0. And I know this is going to be 0. So what I get is, well, do I get 6 over 0? Or do I get 6 over a number that's just really incredibly small? So essentially it's 0. And essentially it is 0, but think about it, it is going to be a very small number. So this is going to blow up to infinity. Question is this positive infinity or is it negative infinity? You know what? I forgot some negatives here. So that 6 was supposed to be negative. All right, my bad. So at least I caught it before the video was over. Okay, so negative 6 over 0. So I've got negative 6, and then we have to think about the denominator. If this whole thing is blown up to infinity, is that number that's close to 0 on the denominator, is it close to 0 on the negative side, or is it close to 0 on the positive side? And it's actually going to be on the negative side. So this one right here, this 2 over negative infinity, notice that's approaching it from the negative side of 0. So what we get is 6 over a very small negative number. Which means that we've got, let me erase this. So what we have here is negative 6 over a negative small number. So the negatives would cancel each other out. So this would actually go to positive infinity.